Okay, welcome to the lecture on standard error, the single sample z-test, and some probability basics. So this is the beginning of the material for the second part of our course, or for the second exam. So if you have not taken the first exam yet, you probably should study and take the first exam before you view this lecture and begin this material, because this will be for the second exam. But we're going to talk first about sampling distributions. Now, there are different sorts of sampling distributions. There's sampling distributions of statistics, and there's sampling distribution of test statistics. But for now, we're going to talk about them in general as a representation of all possible scores of a statistic, be it a descriptive statistic like the mean, or a test statistic like we've already seen, like a z distribution of the standard normal distribution, or ones that we'll encounter in the future like the t distribution, the f distribution, and so on. We've already encountered one sampling distribution, and that is the standard normal distribution. And remember, that was a normal distribution with a mean of 0 and a standard deviation of 1 that conformed to a bell-shaped curve. Now, in general, a sampling distribution can be thought of as a representation of all possible values of a statistic. So you kind of think of it as a histogram of all possible values of a statistic, although the height of the bar or the height of the graphed distribution is not technically a frequency in the case of test statistic frequency distributions, or sampling distributions rather. It's actually called density value, but that's not terribly important for our purposes. So again, the standard normal distribution was a representation of all possible values of z with a mean of 0 and a standard deviation of 1. Now, if in theory, you wouldn't actually do this, but in theory you could create a sampling distribution. They're usually mathematically defined by a mathematical function, as we saw the function for the normal distribution in the first lecture. But in theory, you could create a sampling distribution by taking all possible samples of a given size. So let's say n equals 20. We repeatedly and infinitely sample n equals 20 for a particular statistic, be it the mean or the standard deviation. Let's just say it's the mean for now. And then we calculate the probability of each value occurring, and we could also use that to look up proportions of the area under the curve for a given values, much like we did with the standard normal distribution. Now, one sampling distribution that we're going to talk about a lot in this course is the sampling distribution of the mean. We're going to at least rely on this a lot in the course. So any sample of, let's say, size n, we could repeatedly sample, let's say, size 10. Sample is size 10. Repeatedly sample from a population. Each time we sample from the population, we might get a slightly different mean. So let's say the population mean is 100. If our first sample, we might get a sample of size 10 where the mean is 98. Second sample, we might get a sample of size 10 where the mean is 102. And we might get a sample where the mean is 103. Who knows? We might get a sample where the mean is way out in 70 something, right? So, but for the most part, we'll get probably sample means, if they're taken at random and they're reasonably large, and 20 can be considered reasonably large for our purposes now, we would find that the sample mean is probably pretty close to the population mean, or at least it will bunch around the population mean in a way that we should be familiar with by now, in actually conforming to a normal distribution. So if the samples are taken at random, the mean of all the sample means, so remember, we're repeatedly sampling from the population, so we have sample means. If we wanted to calculate the mean of those means, if we repeatedly sampled, let's say, almost infinitely, right, probably even if we did it like a few hundred times, we would find that the sample mean is basically equal to the population mean, or I should say, the mean of the sample means is basically equal to the population mean. Of course, though, a given individual sample mean may be different from the population mean, and it's very likely to be different from the population mean, and we call that difference, we can call that difference error. So the difference between a sample mean and a population mean, we can refer to that as error. And that there's a formula and a term for this sort of error. It's called the standard error of the mean. Now, if we have the population, if we have knowledge of the population standard deviation, we can calculate the standard error of the mean by taking the population standard deviation and simply dividing it by the square root of n. So the standard error of the mean, the amount we basically expect any given sample mean to be discrepant from its population parameter. The population mean is defined by taking the population standard deviation and dividing it by the square root of n. So we can take a look at this in a sampling distribution simulator. That's not the sampling distribution simulator, that's the normal distribution. Let me see if I can. Okay, I found it. I lost it there for a minute. Alright, so we have here the parent population. So let's say the parent population has a mean of 16. So usually we don't know the mean in the population, but let's set up a situation where we do know it. The mean is 16, and the standard deviation, for now we'll ignore the median, the standard deviation is 5. We want to take samples of size 10, so we'll take one, sample from the overall population, 10 cases. Now it gives us, drops down the mean of those 10 cases. We could do it again. And we'll see that, any given mean might be a bit off from the population mean. All these are working out to be the same, however. There we go. I was thinking they were all going to be exactly the same. So we're sampling, so there's some error involved. So the mean in the population is 16. The mean of these samples of size 10 might vary a bit above or below 16. But what we'll see is if we repeatedly sample and we look at the sampling distribution of the sample means, that's what we see in blue. So I'm just going to skip ahead and do it 10,000 times. We see, or let's do it 20,000 times. So now we've done it 20,014 times. Basically, the distribution of the sample means becomes like a more compact normal distribution, right? So it becomes a more narrow normal distribution because the standard deviation is smaller. Standard deviation is smaller because now this is not the parent distribution. The standard deviation is based on individual scores. So basically, the sample size, you could think of it as a sample size being 1. Now, the standard deviation is based on a sample size of 10. So there's going to be less variability, hence why the normal distribution of the means, the sampling distribution of the means, which is a normal distribution, is less wide, is less spread out because the standard deviation is less. Actually, the standard deviation here of these means is the standard error of the means. So another way to think about the standard error of the means is the standard deviation of the sample means around the population mean. So here we have 1.64 as the standard deviation of the sample means around the population mean. Now, if we use the formula which I showed you on the previous slide, so we'll take the population standard deviation, which is 5, and divide it by the square root of n, which is 10. So I have the standard deviation in the population, which is 5. So I'm going to calculate the standard error of the mean, which we'll symbolize for now like this because we have the population standard deviation. We said it is 5, and then we divide that by the square root of n, which is 10. And we get 1.58. Roughly 1.58 is what the standard error is mathematically in this situation. Now with the simulation, it might be a bit off, but I bet it's rather close. What did we have? 1.64, so pretty close. Probably if we continued to sample, so we only sampled 20,000 times. Let's do 120,000 times. And now we see it's 1.59, which is incredibly close to what it is mathematically, which is 1.58. Let's do another 100,000. And we stay at 1.59. There we go. Finally, 1.58. We've converged on the value with a sample of 520,014 actually repetitions of sample size 10. But anyway, the point I was trying to make here is that basically the distribution of the sample means conforms to a normal distribution, and the standard deviation of that distribution, or basically the difference between the population mean and any given and the observations, the standard deviation of the individual means, the individual sample means around the population mean, is the standard error of the mean, and can be defined mathematically as the population standard deviation divided by the square root of the sample size. Now, if we were to do this with a larger sample size, we would find that the standard error of the mean would get smaller. So let's just quickly do it with a sample size of 25. So with 25, we see it's still basically, I mean, these graphics are limited, but it basically conforms to a normal distribution. But now the standard error of the mean is only 1, right, as opposed to 1.58 as it was before. So with a larger sample, it makes sense we would expect there to be less error and more accuracy provided the samples are taken at random. We could play more games with this, like we could figure out, okay, what will the distribution look like if we sample from a population that's something like this, so very abnormally shaped population. What if we sample from that 100,000 times? What's the distribution going to look like? Well, it turns out it still conforms to a normal distribution. If we were to sample from a skewed distribution, the sampling distribution of the means again still conforms to a normal distribution, with the mean of the sample means incredibly close to the overall population mean, and the standard error of the mean being basically the population standard deviation divided by the square root of n. So you can access this this simulation and play around with this simulation through the slides which are posted on Blackboard. I find that it works best in either Chrome or Firefox. If I try to use it in whatever they're calling Internet Explorer now, it doesn't want to work. So if you can't get it to work in the first browser you try, you may want to try another browser. Alright, so this brings us to our very first hypothesis test, statistical hypothesis test, inferential hypothesis test. And we're going to continue to use, for now, the z distribution. So we can use the standard error to compute z. So instead of, if you look at the formula here, instead of having the standard deviation in the denominator, we now have the standard error in the denominator. And remember, that's calculated by taking the population standard deviation divided by the square root of n. So we now have the standard error in the denominator, and now instead of having an individual score to the left here in the numerator, we have a sample mean. So we're simply taking the sample mean, subtracting the population mean, and dividing it by the standard error of the mean to basically find out, okay, how much difference between a sample mean and a population mean is there if we take into account the amount of error we expect. So as is the case with almost every equation for an inferential test that we'll use in this class, the numerator represents kind of like a signal, an effect, and the denominator represents noise. So we want to see, do we have more signal than noise? Do we have more effect than error? So to do this sort of test, you need to know the population mean or have really good evidence of the population mean. You have to want to compare a sample mean to it, basically to see if it is different from the mean of that population that you're comparing it to. You should have a random sample, although with humans that's pretty hard to accomplish. And we basically can ask, what's the probability of finding this sample mean in a population with a mean of the population mean? So let's say the population mean is 100, our sample mean is 95. We can ask, okay, how unusual would that be? What probability is there of getting a 95 sample mean if the population mean is 100? So in other words, we can determine how unusual or extreme a sample mean is with the specified population parameters, mean, standard deviation, and sample size. So here we kind of have an example of that where we can look up a particular z value that will be the result of the z-test, just as we did before when we calculated z-scores. It's almost the same process, just the formula is a little bit different, and the situation where we might use it is a little bit different. But basically we can ask about the probability of a given sample mean from a given population, and we can figure that out by using the proportion of the area under the curve to answer that question for us. So the difference between these formulas is kind of slight. At the top here we have the z-test formula, which again has the sample mean minus the population mean over the standard error of the mean, and the formula at bottom is our z-score formula, which has an individual observation minus the population mean over the population standard deviation. So use the formula at bottom when you want to compare an individual case to see how discrepant it is in standard deviation units from the population mean, and you use the formula at top to basically test to see if there is a difference in between a sample mean and a population mean in terms of standard error units, really. So let's try it. Let's compute one of these. Let's say someone named Christopher. This is obviously just kind of like a made-up data, but Christopher claims the students at his school possess superior intelligence to the general population. He randomly selects 22 students from his school. He administers an IQ test to each student and finds the mean score to be 109. The population mean for this IQ test is 100, and the population standard deviation is known to be 15. Is his claim supported by the data? So we want to conduct a z-test here. We have the information we need. We have the sample mean, which was 109. We have the population mean, which is 100. We have the population standard deviation, which is 15, and we have the sample size, which is 22. So we have the information needed to compute the z-test. So first thing you should always do when you're doing something like this by hand is to write down the formula. So the z-test formula, I'll just put test there to differentiate it from the z-score formula, is x bar, which is the sample mean, minus the population mean, which is mu, over the standard error of the mean. Now remember, the standard error of the mean is standard deviation divided by the square root of n. So let's go ahead and do this for this problem. We have a sample mean here in the question of 109. We have a population mean of 100. This is all given in the question. And we are dividing that by the standard error of the mean. So to get the standard error of the mean, we have to take 15 and divide that by the square root of n, which in this problem, I believe that was 22. Yes, 22. So the numerator is easy. The numerator is going to continue down here. The numerator is 109 minus 100. That is 9. So his school, the average IQ was 109 compared to the population average, which is 100. Is his school's IQ higher than the population average? So we want to divide that by the number of standard error, or the standard error estimate. So to do that, we take 15 and divide it by the square root of 22. So if you divide 15 by the square root of 22, I get 3.1980. It's 3.1980. So now we take 9 and divide by 3.1980, and we get 2.81, roughly 2.81. Okay, 2.81. What does that tell us? Well, it tells us that these means are 2.81 standard errors apart. The sample mean is 2.81 standard errors higher than the population mean. Is that unusually high? Is that so high that we might conclude that there is what might often be called a statistically significant difference? So you can consult a z-table or use an online z-calculator to determine that. So there, now we have the calculator. That's what I wanted that there for. Alright, so let's say we have a normal distribution. We'll leave this as a standard normal distribution. Won't mess with this. Leave the mean at 0 and the standard deviation at 1. And we'll ask, what's the probability of getting a score? Basically, we want to see what's the probability of getting a score 2.81 or above. And we can see that probability, as you can barely see what's shaded there, probability of getting a score way out there is 0.0025. So it's less than 1%. It's like a quarter of 1% of the time. That would happen if there really was no difference. If there really was no difference between the population that he sampled from and the general population, we'd find a result like this less than 1%, much less than 1% of the time. So what we would probably conclude is there is enough evidence to support his claim. There's enough evidence, even though there is still some probability that there's no difference between his population and the population that he's comparing it to, the general population. It seems like that would be a really unusual situation where we'd find this difference just by chance, right? So it's 0.0025 is the probability of finding this difference if there is no difference at all, right? So we're going to conclude that Christopher is correct because the difference he found was really unusual if there was no difference at all, or if there is no difference at all. Now I know that's kind of convoluted. We'd much rather rather know the probability that there is a difference rather than say this is the probability of finding this difference if there is no difference at all. But unfortunately, we usually don't have a way to calculate the probability that there is a difference. So you can think of this p-value, although this is the probability of finding the difference we detected if there is no difference at all. If you want to just make it easy for yourself, you can just say this is the probability that this difference is due to chance. It's not 100% correct to say that, but it's fine. It's easier for your own sanity sometimes to think about it that way. So what we just did, you should be very excited. I know you didn't know it while we were doing it, but what we just did was a null hypothesis significance test. We just tested a hypothesis using a fairly basic inferential statistical test called a z-test. So we've already, well, actually, I should say the z-score from the z-test. So I don't want to confuse you because it's a little bit different from a straightforward z-score. But the z-score from the z-test tells us how many standard errors the sample mean is from the population mean. So this is a inferential test because we are trying to make a decision based upon the sample, so the sample of 22, and the sample mean about the difference between the populations. Is there a difference between Christopher's school population and the general population, or is there no difference? So the null hypothesis, and we're going to talk more about this language of statistical hypothesis testing in the next chapter, but for now I want to introduce the null hypothesis in this context as stating basically that there's no difference, where the difference between Christopher's school population and the general population is 0, or that there's no difference. And the alternative hypothesis that he put forward says that there is in fact a difference and that his school population has a higher IQ than the general population. So what we did was we examined the probability of the results given that the null hypothesis was true. So that value that we got, that 0.0025, that tells us what's the probability of these results given that the null hypothesis is true. So in other words, we asked what's the probability of finding the sample mean that we found if the population mean for intelligence at the prep school is not different or is equal to the general population. Since that probability was very, very small, we then rejected the null hypothesis and we decided that there was in fact a difference such that Christopher's school possessed higher levels of IQ than the general population. All right, so let's do one more of these before we move on. Alright, in this problem it says, assume that it is known that the mean number of gallons of gas consumed by non-commercial drivers in the United States is 593.35 gallons. Further assume that the population standard deviation is known to be 96.62 gallons. A random sample of 150 drivers from deep South Texas is taken and the sample mean is found to be 564.17 gallons. What is the probability of finding a sample mean that is this different or discrepant from the population mean? Should we conclude that these are significantly different populations in terms of gallons of gas used? So we're going to apply the z-test to this question. So we have to locate sample mean, population mean, standard deviation, and sample size. And once we locate those, we simply plug them into the equation for the z-test, like so. So here we have the sample mean, 564.17, population mean, 593.35, and then in the denominator we have the standard error, which is 96.62, and then finally that's divided by the square root of 150. So let's go ahead and calculate z. Z observed or z obtained will be 564.17 minus 593.35. It's going to give us negative 29.18. So that's our difference between the sample mean and the population mean. And now we want to determine our standard error. So in a sample size of 150, how much difference do we expect just by random error? I get 7.88. 7.888. We could put 7.8890 if we round, I guess. Or actually, rounding error, 7.8889, but 9 should round up. There, rounding. Alright, in any case, as long as you're in the ballpark of rounding error, you're fine. So now, we simply divide negative 29.18 divided by 7.8890 gives us negative 3.70 in that ballpark. So negative 3.70, I'm rounding here, so your number might be slightly off, but that should be okay. Negative 3.70 in a normal distribution, which we're assuming here, because it's a sample mean, and sample means, as we saw in the simulation, almost always conform to a normal distribution. It would be way out here, I don't know, 3.7 would be way out here on the tail, negative 3.7. So the probability of finding that, so we're going to look up the probability in the tail, is going to be really small. It's going to be really unusually small probability. So let's go ahead and look that up. So you can use a table in the back of your book to do this, but I like these calculators. They make this pretty easy. So what did we get? 3.7 negative, right? That's important. Negative, below negative 3.7. That's going to be in the tail. We click recalculate, and we got 0.001, right? So this is a really unusual difference if there is no difference at all. So we're going to conclude that there is, in fact, a statistically significant difference between these two populations. I guess the general population, gallons of gas used, is significantly higher than the sample from South Texas. So we're going to assume that there is, in fact, a significant difference based on this statistical test. There's a significant difference between these means, such that the general population has more gas consumption than the South Texas sample. All right. Now it asks, okay, do the calculations again, but let's just pretend instead we had a sample size of 30. So we just had a sample size of 30. Things would change. What would change in particular is the numerator, our standard error estimate. So we have to now, in the numerator, so almost everything's going to stay the same. So in the denominator, we're going to change the standard error estimate. But in the numerator, we're going to have still negative 29.18. But now we're dividing that by 96.62 over the square root of our new sample size, which was what? 30. Over the square root of our new sample size, which is 30. So we take 96.62 divided by the square root of 30. and we get 17.6403. So we have z equals negative 29.18 over 17.6403 and I get 1.65, or negative, that's important, negative 1.65. So what happened here is because our sample was much smaller, was 30, our standard error, as you'll notice, went way up. So our standard error before was 7.88 because we had a large sample. Now with the same situation but a much smaller sample, our standard error is 17.64. So now our z value is negative 1.65, which is likely going to be a lot more probable than the last one we entered, right? So we want to below negative 1.65, and we recalculate, and we find that that would happen about 5% of the time under the null hypothesis. If there's really no difference at all, we might find a difference as extreme as the one we detected, given our standard deviation and our sample size, about 5% of the time. So that's a bit more likely to occur. Whether or not you want to say there is a significant difference here, it's a little bit more fuzzy. So 5% of the time, is that unusual enough for you to say, yeah, there's probably a difference, or do you need more evidence? So would you prefer it to be like 0.001% of the time or something like that? So it's really a judgment call here, and we'll talk more about this next semester when we not next semester, next lecture. Next lecture when we cover inferential tests, and we'll talk about how to decide or set up a decision rule to decide if you want to consider the difference to be, quote, statistically significant or not. For now, we'll just say the probability of this occurring, if there really is no difference between these two populations, the probability of us detecting the difference that we did detect just by chance, let's say, is about 5%. Alright, so I'll post an additional example on Blackboard of a z-test if you want to review it, an additional example. For now, we're going to switch gears a little bit and delve into, very gently delve into the world of probability. So this course doesn't have a very strong emphasis on probability. If you take a statistics course in a math department, it may be actually called Statistics and Probability or Probability and Statistics. As you might have already noticed, probability is an important part of this course, but we're going to study it more in conjunction with hypothesis testing than probability for the sake of studying probability. But there are some things that we should at least very briefly go over. Alright, first and foremost, let's define the probability as the likelihood of an event occurring. So that event could be, you flip a coin, it lands on heads, or you flip a die and it lands on 3, or it could be the probability that somebody will get in a car accident. So it's basically, could be anything. An event could be anything, but it's basically the probability of the event occurring. Probabilities range between 0 and 1. 0 means the event has no chance whatsoever of occurring. 1 means the event is definitely going to occur. Where usually when we're talking about probabilities, we're not talking about 0 or 1, like all or nothing type things. We're usually talking about somewhere in between. For an example, a fair die, if you were to roll a fair die, so just one, the probability of rolling a 3. So a 3 is one side out of 6, so that probability is 0.1667. Or a coin, if you were to flip a coin and it's a fair coin, the probability of getting heads would be 0.5, where the probability of getting tails would be 0.5. Right, so let's say we want to determine the probability of 2 or more outcomes for a given event. Right, so there's still one event, But we want to know what's the probability of 2 or more independent, that's an important part, independent events. So something like, what's the probability of getting heads or tails in one coin toss? Well, that's easy, right? It's just 1, because if you toss the coin, it has to land on heads or tails. So 0.5, although there was that one case, I think, in a football game where it landed on its side and they had to retoss it. Well, let's just pretend that that can't happen. So it would be 0.5 plus 0.5 equals 1. Or what's the probability of getting a 3 or a 6, in one die toss? So just 1. What's the probability of getting a 3 or a 6? And that would be 0.333. Because you could basically, you could just add the two probabilities together. The probability of getting a 3 would be 0.1667, and the probability of getting a 6 would be 0.1667. So adding the two probabilities together, you would get 0.3333, whatever. So 1/3 of the time. So if we're talking about independent events and we want to know the probability of 2 or more independent events occurring, but this is only one event, so this is not 2 events occurring together. This is the probability of 2 or more events. What's the likelihood of one of these 2 or more events occurring in a given outcome? Then you can use the addition rule, which is to simply add the probabilities together. The multiplication rule is for joint probability. So this is multiple events occurring at once. So we want to determine the probability of individual events occurring together. So this is 2 or more events occurring together that are independent of each other. That's an important point. You can multiply the probability. So if you toss 2 dice, what's the probability of getting 2 5s? So you could take the probability of getting 1 5 and multiply it by the probability of getting another 5, or simply square that, and you would find that it is roughly 0.027. So you just multiply the two probabilities together, or square the probability of rolling a 5. And if you do that, you'll find that it's roughly, the probability of that is roughly 3. It's 0.027, or it would happen about 3% of the time, a little less than 3% of the time. If a coin is tossed twice, what is the probability of getting tails twice? So we can use the multiplication rule to basically just take 0.5 times 0.5, or 0.5 squared, and find that it's 0.25. So about 1/4 or 1/4 of the time, if you toss a coin twice, you will get the same outcome. What about if a coin is tossed 10 times? If a coin is tossed 10 times, what's the probability of it falling on heads every single time you toss it? So to do that, you would need to take 0.5 and take it to the 10th power, which is basically like multiplying 0.5 times itself 10 times, right? And we would find the probability of that is really quite low. It's 0.0009, or 0.0001 if we round. So it's really unlikely. So to get the probability of tossing a coin 10 times and getting, so probability 10 heads in 10 tosses, right? So we toss the coin 10 times. That probability is going to be 0.5, since these are independent events. One toss does not affect the other, to the 10th power. So 0.5 to the 10th power gives us 0.00097. So pretty unlikely. So maybe 9 times out of every 10,000 times you tossed a coin 10 times, right? So I don't advise you to sit there and do it, because you might be there all day before that actually happens. It would eventually happen, but it would take a while, most likely. It could happen the first time, right? But it's just really incredibly unlikely. All right, so the additive rule for independent events we use when it's one event and we want to know what's the probability of some number of outcomes. We add those probabilities together. The multiplicative rule is if we want a joint probability. So the probability of two or more events co-occurring. So with the multiplicative rule, it's the events are co-occurring. With the additive rule, it's just one event, but we want to know out of these possibilities, what's the probability that one of them would occur. All right. One more type of probability I want to talk about. We've already talked about joint probability when we talked about the multiplicative rule. And joint probability, again, is the co-occurrence of two or more events. So, for instance, looking at this table, although these things are not independent, so this calculation did not really make a lot of sense to do here, but if, let's pretend, wearing a seatbelt and being a parent were independent. If they were independent and we wanted to say what's the probability that we select randomly from these 100 cases, what's the probability that a person would be a parent and a seatbelt wearer? If we want the joint probability, and if they're independent, which they're not, but let's just pretend they are, we would take the probability of being a parent, which in this data set is 20 out of 100, and the probability of being a seatbelt wearer, which in this data set is 30 out of 100, and we would find that the probability of randomly selecting someone who is both of those things in this data set is 0.06. That's if those things are independent, which they're not. We've already acknowledged they're not independent. Conditional probability, on the other hand, is what's the probability of an event given that another event has occurred, or provided that another event is assumed to have occurred, right? So we might ask, what's the probability of being a seatbelt wearer given or provided that one is a parent? So that's already assumed or provided. So to do that, we would just simply look at the parents and see, okay, that's 15 out of 20, that's 0.75 probability, right? Conditional probability, something is given and we want to look at what's the probability of some other event given that another event has occurred. So looking strictly at parents, what's the probability that a person at random would be a seatbelt wearer, and that's 15 out of 20, 0.75 probability. All right, finally, probability underlies all of the statistical hypothesis tests that we'll cover. And basically what we're going to be looking at a lot is what's the probability of these results that we found, our sample results, just like we did in the z-test in this lecture, what's the probability of what we found if there really is nothing in the population, no difference, no relationship to the variables, right? So we're repeatedly going to test the null hypothesis by using this conditional probability. What's the probability of our results given that the null hypothesis is true? If that probability is very low, we're likely going to reject the null and claim that there's some sort of difference or relationship between variables. If the probability is too high, then we're not going to be able to say we have enough evidence to reject a null, and we're not going to be able to say that there is a relationship or difference between variables that we're testing. All right, I hope you enjoyed that lecture as much as I have, and I'll see you, or you'll hear from me in the future.